So this second goal also is to prove the dual functor, this Laplace functor, is equivalent to its right term when respect to this Castello part. So Dennis in the morning he did this left term. Whatever he did, you may forget. So it has to do this lower commutative diagram. He calculated some comparison all these things for us. So what I'm going to do for this goal 2, as you may guess, it has to do with the upper commutative diagram. And let me draw it. And now restrict to this hospital part. So I will use this log test to denote the computation of localization followed by projection onto this hospital part. So claim 1, this is a quotient function. So it's kind of follow from goal 1 because classical things that are clearly supported on some quasi-compact open and by the first claim, so you will see this. The right hand side is the function from neuromorphic opens to Q on this reducible locus of teacher local systems. So note that here we can also use indical node, but they give you the same thing because we restrict it to the reducible part. And this is the Poincare effect functor followed by the projection. So I will just write it as Poincare and irreducible. So maybe this is write Poincare effect irreducible. So and the horizontal thing is our SOE, which is an equivalence. And here our function is this L cast. This is the function we want to study, and our goal 2 is to show the dual of this L cast is equivalent to its right adjoint via the self-duality on these functors or on these calculus. That's our goal. So, and now I will make a claim. So it contains 2 parts. So the first part is everything above is every cat above is self-dual. In other words, all 4 categories are self-dual. And via these self-dualities, we can talk about conjugate functions for these functions and view them just as functions between the same categories. And the second part is say every function is self-conjugate. So in particular, it will imply that L cast is conjugate to itself, which then we will see is just means L cast dual is equivalent to its right adjoint. So I made these 2 claims and I'm going to explain them. So we start from categories and then we do functors. So any questions so far? Let's do them one by one. So this KL is due to KL dual as before the break. I even told you the unit object. So then let's do this decast. So in Dennis talk, he explained this decast is due to itself. So the idea is it's still given by the real duality. So because cast, so they are clearly extended from some quasi-compact open. You don't need to worry about non-quasi-compact of G. So these are easy. And can we also say this to call on reducible part is also self-dual because it's the usual revealed duality on control. So it's done by Dennis before. And now the thing we really need to deal with is this indical star or monogamy Fourier opens. Is due to itself. Note that this is actually a structure rather than property. So you really need to provide a self-duality on that. For instance, you should either provide the parent function or the unit object in the tensor product. So, but here we can cheat. So if you cheat now, you will pay a price, pay a fine. So let me first tell you what's the cheat. FLE is an equivalence. So this means if your source is self-due, then your target is self-due. Just translate it via FLE. Tells you that 1 actually implies 4. So that's something you can check. But if you use that, you essentially just black box the duality, self-duality of these things into the definition of FOE, and later when you try to prove something, you will be in trouble. Like if you want to prove the function is self-conjugate, you have to do something. So this is like how to think about it. The actually self-duality of this is much more complicated. But let me try to say something about it in this small region. So in general, so this indical of finite capsine is self-due. And now if the capsine, so this indical star is due to indical shrink. So I hope we have defined indical shrink before. If not, just imagine you replace all star products by shrink products. And that's the definition. Okay, this is the definition. Yes, but yeah. So in the world of indical star, so we have the ability to do global section functors. Therefore, in the world of indical shrink, we are able to do this dualizing shift. And similarly, indical star on something is a comonomial category, but indical shrink is a monomial category. And it's not hard to formally see that this indical shrink actually acts on indical star. So as an monomial category acting on some module. So therefore, if you want to provide a self-duality, what you really need to do is try to find an object here and using this category to act on it to obtain a function. So you need to find a particular object here. Yes, the fake dualizing shift. So you need to find something called F fake in this indical star. So it's like in indical shrink, you have omega, but in indical star approach, you don't have. You have to define something maybe in an ad hoc way that called omega fake and try to show the function obtained by them as an answer. And this is indeed possible for this guy, but I don't have time to explain. If you want, this is in GOC2 in some section. Yeah. Yeah, but that's the actual construction. And if you want to prove this thing is self-conjugate, you have to do that. And maybe we'll come to this. And are people happy with that?
You just mentioned this. When you put self-conjugacy, there is some local part which is.
Yeah, we will see that.
Can I roughly think that like you kind of need to it's like the endomorphisms of actual WoW modules is you kind of be anchored, like kind of
Yes.
each thing into like
Yeah, you can see that. Yeah, you
that's
can see that.
basically
Yeah, but yes, I can also just look at those geometry.
sure. Yeah, exactly.
The person sitting next to you was the guy who invented what's dimension for
Yeah, it is. You feel like the dimensions will be
The guy sitting next to me and then they talked about what he forgot about.
Okay, so let's come back to functions. We need to show these functions are self-conjugate. So let's first look at FOE. So this FOE is fine if you use this chip. If you use this chip, so by design, so the self-duality on the source is come from that on the target. So therefore this function becomes self-conjugate. But if you do it in the correct way, this is something you need to prove. And how to prove it, you need to invent a time machine and go back to Tuesday and ask Dennis to prove it when he gave his talk on FLE. But I can't do that. You need to find something. You need to define. I'm not going to.
You know what it is?
Yeah.
Like morally, you think each while module extend it as much as you possibly can.
And more precisely, you take the CDO and you apply a DRSP on one side, because critical to blob reductions. Yes. Critical to blob. Yes.
That's the answer.
So it was, in other words, the CDO was a bi-module, and you heat up on the bi-module. What was
Okay, so now let's look at the localization function. So before the break, we explained that this loc itself is self-conjugate when you look at this quasi-compact open. So therefore, it's easy to deduce that this guy is also self-conjugate. So there's this projection to capital thing, but you can easily deal with it. So let's believe this. So therefore, I claim we only need to show this guy is self-conjugate if you want to show L cusp is self-conjugate. Then you write down the claim. So this concrete irreducible is self-conjugate. And claim 8 is this L cusp is self-conjugate. And it's easy to see 7 implies 8 because this function is a quotient function. So if you want to say this function is self-conjugate, you can compose with any quotient vector. As long as this quotient function itself is self-conjugate, you only promote this diagonal function is self-conjugate. Then you can just say each function in the accommodation is self-conjugate. So therefore, this implication is good. So what we now really need to do is this statement. And as long as we can do this, we win because here's an easy exercise. Actually, I will just write down how to do this. The self-conjugate tells you that this function is returned to this cusp. But by definition, this is you first apply right joint and make U, and you can do U back. So it tells you the thing we want. This is the proof of GoTo. So what I did is I explained how to reduce GoTo to this statement, which tells you that this concrete set is self-conjugate. Any question so far? So if you want, you can also do it for this diagram. It's easy to see. This same logic, formal logic, allows you to deduce Stanley's claim to self-conjugacy of the automorphic concrete function. In other words, you need to show concrete should be equal to concrete fact. So that's the logic in Stanley's talk. But now let's do the spectral concrete. So let me remind you what's the definition of this spectral concrete. So I need to draw. I will use the. I need to draw some correspondence. So here, this is our log-sensitive check. This is what we call log-sensitive check. Monogamy free. No. Oops. On the run space. This is off G check. On the run space, monogamy free. So we call this classified as operas on puncture disk such that the local systems can be extended to the disk. This classified operas on puncture curve such that the local systems can be extended to the entire curve. And these are just natural projections. And recall this, let me give a name for them. Let me call this pi. This is S. So recall we are doing cuspidal part. So what we really need to do is to base change this picture to the irreducible locus. And let me draw it like that. So let me call this pi prime. So this is pi. Okay, so pi prime. And that's a fiber product. So each I will just write of the check run monogamy free. So no irreducible. That's something here. So and the structure map. So let me giving a name for them. So this is our S prime. So by definition, we know what's this Poincare irreducible. So this Poincare spec is given by star pull along S, followed by just star push along this pi. So when you restrict to the irreducible locus by base change, so you know it's just given by star pull along this S prime, followed by star push along this pi prime. So far so good. So then, just like what I told you, so you may say its conjugate factor is obtained by replace all these stars by shrinks. So this is something very reasonable, which is indeed true if you be very careful about indical star versus indical shrink. So namely, so if you do that, even to have the definition of this shrink pullback, so you need to use indical shrink. But now we are discussing self-duality on this indical star, and more or less by design of this definition, so this shrink pullback on indical shrink becomes star pullback on indical star. I'm just saying you should safely ignore this part because it's something in the black box that we didn't explain. So what really matters is to compare these two functors. So the local part, so it's a monster that I don't want to talk about. I want to compare these two direct image. So and this is the thing we want to do. So we only need to show these two functors are the same, and we will prove this.
Five times what you can do. Popular partially defined left to join 5 times.
Yes.
Okay.
So if you remember, this map is very nice. It's finite. It's next. Right. So therefore, this upper street is defined.
Yes.
Yeah.
But the 5 times lower street says.
Yes.
Justified.
Yes.
Okay.
And it's justified by the following lemma, which says that this pi prime is proper. And if some map is proper, of course, a star direct image equals to a straight direct image. So, and if we can have this, so we know that these functors, so they're equal to each other, and which is claim 7 on the board above. So we have just reduced GO2 to this lemma. So far so good. Okay, and I'm not going to give you the precise proof of this lemma. So it's some geometry that we haven't discussed, but let me give you some rough idea about how to prove this lemma. So recall in the definition of this opus, so we talk about some B-check reductions to the local system. And we require this reduction in some sense to be in a generic probation. So we require some sections to be non-zero. You don't need to remember what are these sections. It's just saying something is non-zero. So this B-check reduction, so itself is classified by some modulus stack that is proper, because we know that stack variety G-check mod B-check is proper. So therefore, the thing we need to deal with is this non-vanishing. So in other words, if you ignore that condition, if in the definition of opus, you just ignore this non-zero condition, the modulus stack you obtained would be proper over this no-access G-check. So I'm just giving you some rough ideas. I'm not trying to make things precise. So now the claim is, if you look at irreducible local systems, actually, so every B-check reduction automatically satisfies this non-vanishing conjecture or non-vanishing condition. So these sections would be automatically non-zero. Because if it is zero, so let's see the most extreme case. So like all these sections are zero. Then, as Dima told us, it means your B-check structure is actually, your B-check reduction actually gives you a B-check local system on the entire C, which implies your local system is not irreducible. So similarly, you can imagine if part of these sections vanish, you will obtain some p-check structure on your local system. Here, p-check is some parabolic. So that explains why this irreducible thing allows you to say this map is proper. So are people happy with this argument? So some you want to say something more?
Well, Kabir was confused. I think he was actually thinking out the geometry a little bit. So just like for SL2 or something, the upper structure is basically some kind of line that's narrow from the curve. And so this is some kind of crazy infinite dimensional projective space that looks like some kind of projective space applying to the curve. And that's problem. And then passage from the GL2 to the SL2 to the general projective group. That's exactly what you said about actually listening to them.
Yeah. Okay, so then let's just believe this. And because of that, so we have finished the second law, which tells you that the dual function of LG cusp is equal to its radal joint. So any question? Now let's do the last one. So first, let me tell you what's this space that you want to take homology for. So it's the inverse of the image of pi prime at your local system sigma. Here, this pi prime is the map from this global homology free opus to your local system. So we just take the fiber of this map and take homology. So take, in the topological sense, you obtain something which is the fiber of AG. So this is the claim. And now I will spend some time try to sketch the steps for proving this. And I will leave another black box when doing this.
Sorry, so the last one stupid question to get something. It says if I take open structure with no hole, the place is closed thing that it blocks this.
Yes.
And then now it's like I want to pick points and allows them to be all at the points. That would still be just an actual finite dimensional thing mapping completely down to log this and taking some like hole limit over allowing more and more holes, and that's what gets the type of thing the same. That's roughly good.
Yeah, that's roughly
It was a picture, although when you allow no holes, it would be infinitely greater than equal to 2 for it to be a natural close. If you're already at still fully closed, you just wouldn't.
I think this time is
Much
not
easier
for
to see
the
it's closed.
examination.
Much easier to see it's closed because of that shape.
Okay.
Yeah. We can leave that to the session.
Good, thanks.
And now let's do this the last one. I will erase this. I want to keep this up. It says S prime. So now I will change my notation. I will just put this prime as S. So this is our diagram. So I will write down some equivalence and try to explain something about it. So, but before that, let me tell you where we are. So we want to calculate this A. So we are on this diagram. So let me use some color chalk to draw the address. Oops, we don't have them. Okay, then I have to. Yes. So here, this Poincare reducible, so it admits a right joint. Yes. So which is let's call it just for F reducible. So it's a continuous right joint. And this FOE, so they all admit inverse. And this L cusp, so it admits a vector joint. And this log cast that can make a vector joint called gamma cast. So which is fully faithful. So I'm not claiming any directions on this diagram commute. I'm just saying the left joint commute with left joint, and the right joint commute with right joint. So that's what I mean. And now I will do some diagram tracing. Do this diagram tracing on that code. This algebra AG class tensor ring method by definition is given by you first apply this vector joint and then wait, did I mess up with something? This is moment. I'm confused. I'm doing. Aha, so yes, this I mean the theory. So this is like LL test. This L test. So this is the definition. And we have already proved that this LL is equal to LR by some by comparing them with with the two functor. So we only need to calculate that. But when doing this, we lose the monomial structure on the first line. So therefore, this is just as in the function as in the Wolfram's. So in other words, here this description is just as vector spaces as vector. So I'm not claiming anything about the multiplication structure on this A, although there's a way to do that. So I'm just calculating it as a vector space, and that's enough for Kevin's talk, I think. So we only need to do this LR followed by L. And now let me do some diagram tracing. So I will draw pictures instead of write down the names of these functors. So this thing is just go that direction and go back. So it's equivalent to the following thing. So you can apply this right joint and this right joint and then do localization and this cast. I can name that the same. So we have both. So name is equivalent to this picture. Academic, they are the same. That's because the gamma cast is fully fixed. So you first apply some fully fixed functor and then you project back. That's nothing. So this is because the gamma cast is fully fixed. So this is the first step. And now, because the commutativity of this diagram, so we can do the other, do it along the other arc, we can go up and go left and then go back. So this is returning to that. I guess people know about these functors. And because this SOE is invertible, so when you go leftwards and back, so what you really did is you go up and go back. So what I just said is to calculate this AG cast is enough to calculate the value of this composition, this functor on say the structure sheet on this Moses G-check irreducible. So therefore, what we really need to do is we want to calculate this for F irreducible followed by this concrete irreducible. And we want to calculate on the structure sheet. So this result will be this AG cut. and this is something we want to calculate. So so far so good. And now we are notice that we are purely on the spectral side. So this is something internally about this diagram. So namely, if you remember the definition, so the function on the right hand side is given by pi upper streak followed by s lower star followed by s upper star followed by pi lower streak. Here I recall that this pi is proper. So explained in second ago. So this is the function we want to calculate, and we want to apply it to the structure shift to calculate it. And we want to see its fiber is still like an homology. So this is what we want. Now I will do two propagations. Prop 1 tells you that when you do this function, in fact, you don't need to do this S. So there's a natural transformation from this guy to this pi lower shrink, pi upper shrink. And the claim is this is actually an equivalence. So if you want, so Dennis would say, so this one thing, when you do this integration, so it erase the difference between the novel and novel. So that's the word from the paper, but I don't really understand why. What's the precise meaning of that? So I don't have.
Well, it's run magic.
Yes, it's run magic, but I don't have intuition for that. Maybe later or Nick will give you some intuition for this. So by intuition, I mean picture from topology, like disks and fusing, all these things. Yeah. Like physics, they will draw something to say this is obvious, but I can't. So proposition 2 has to do with this map and the RAM version of that. So which means the following. So let me draw it here. So this is LS G-check irreducible. So the source is something which is horrible, but monodromy free, removable, irreducible. So in the middle of them, so we can considering the formal combination of this thing over that. So this is something we want to consider. So this might look too horrible, but let me write it like that. So in other words, an indicode on this guy is really an indicode on top equipped with a connection along this fiber. So this might look too horrible. So therefore, I will just base change along sigma, and I will tell you. So what's the thing? So this becomes the fiber of sigma. So I'm tired of writing down all these. I will just call this op sigma. Maybe op sigma 1. So this is the fiber. Then this is just the RAM space of that suit. So I'm considering this guy. So in other words, object here are just in the coherent shifts. Object here are in the coherent shifts with connections along the fiber. So let me give names for these maps. So this computation is our pi. So let me call the first map. What's a good name for the first map? Let's call it iota. And the second map, let me just call it this one. Okay.
So when this both sigma run, I can really say a point of it is basically like few points.
Yes, I'm about to say this.
Right.
So what's this stack? So it's class. You fix a global local system. So it classifies generic open structures on this local system. So here, generic means you are able to pick up some points and considering the complement of these points, this puncture curve, and you only need to define an open structure on them. But you need to remember the points you removed. So that's the definition. So now I'm going to say the following. So here the proposition one says you only need to do this pi up shrink and pi lower shrink. So which is this map. So this pi upper shrink and pi lower shrink, it admits a natural transformation to this pi upper shrink followed by direct image. So given by this adjunction. And then this is also ISO. So let me tell you what this means. So first, let's don't look at that. Instead, let's look at this picture. So which is much more clear. So let's just base change everything to the sigma and try to understand what's happening. So this pi upper shrink is you shrink pull back to something here and then go down. In other words, so I will say it's pop to prime. In other words, you see that this end and in the top of this omega on this op sigma 1 is equal to you first pull back on this map and then do direct image. In other words, the endomorphism are D-modules. So its end as D-modules, maybe write D-modules because we are omega of the same object. So by the way, end of omega by definition is the homology of your stack, which is the homology of this of G. So sigma. So that explains why we have this calculation, because you just combining these two propositions. So previously we want to apply this endo functor on this O. For simplicity, we base change at the point. We want to apply this functor and therefore this functor to this O, which is to apply this pull push at K, which gives you that. So this explains why proposition 1 and proposition 2 give you the circle.
So in other words, it's sort of a very, maybe to recap for a second.
Yeah.
So the left-hand side here is essentially functions on the space of operators at some kind of coherent cohomology groups. And the right-hand side has Durand cohomology groups. And this space of operators is a weird thing about the particular geometry here, doesn't matter about operators, but about these weird rational maps that coherent cohomology and Durand cohomology coincide. And it's just, and it's a very non-trivial thing in this proposition 2 prime. So just maybe to emphasize a little bit more, like everything that's happening on this top left diagram and that top right diagram, it only sees coherent sheaves on the space of operators. But now all of a sudden we're saying some calculation about coherent sheaves is actually the same as calculation about modules on the space of operators. It does not occur naturally in these kind of diagrams.
Yeah, exactly. So this looks some magic to me. So it's another magic in the paper. So Dennis would say, so doing this Run integration erase the difference between shifts and local systems. Yes, consequent shifts and D-modules. Okay, so
and maybe just one additional comment for anyone who wants to play with the things a little bit. So when at some point in my life, when I learned what it means for a pre-stack to admit deformation theory, I was told all pre-stacks that come up in nature admit deformation theory. Right, Nick? But these spaces of rational maps don't admit deformation theory. They don't have well-behaved tangent spaces. And somehow related to this that in the potential way. If you thought like maybe you should have seen some cotangent vectors coming out, you'll actually realize those didn't actually even make sense.
I just figured this is a good way. You're saying the answer could depend on more things, but the end of the interview is less than a equal to.
of course, yes. That's like this exponential. Yeah, but this omega is not enough. That's not the usual one.
Well, and like literally speaking, is like we don't expect the global sections of omega. That tends to be like you're getting on.
Oh, that's not in the heart.
Yeah, I don't know, you're getting more than comfortable making ways and pretty crazy.
But it's. So what's the question?
It's weird because they want to.
Yeah, but you also need to take two. Sorry. That's a duality. Sorry. But I forgot to take two. Yeah, so I think now you are happy.
I'm happy, yeah, that's good, thank you.
Okay, so this proposition one and proposition two, they have nothing to do with special properties about operas. So in fact, it works for any D scheme such that this G check mapping to B G check. So as long as this map is affine, you can define all these things, and similar claim still works. So in other words, what I'm saying is for any one to Z, I'm going to write down two propagations. But for simplicity, I will do the absolute case. I will just consider you have a D scheme Z over this X, affine D scheme. I will just rewrite these propagations as some general claim, but give you no explanation for them. So then maybe Nick will say something about intuitions behind these propagations. So now our diagram becomes the following. So this looks is reducible, so it's just a point. So we can get rid of it. So here, this is horizontal sections, not from the entire curve, but from the puncture curves, x minus x. Here, this small x is a moving point on your run space to your z. This is some space over run, and this maps to so horizontal loops of your z. So we have this diagram, and this is the map S. And now what propagation one says? The propagation one is still the same. But I don't need to repeat this data. So it's still the same. So propagation two, as Sam said, so it just tells you that pi upper shrink and pi lower shrink is equal to pi upper shrink in the dimensions and pi lower shrink in the dimensions. So here, there's the Dirac space of that. This is pi1, and this is pi. So these are the two propositions that work for general D schemes, but I can't explain the equation behind them. So, but let me say something about them if you want to prove it. So for the first thing, so essentially, so you have all the ingredients to prove that. Like remember, so this is controlled by some commutative fraction algebra, and yesterday I explained to you how to calculate the functions on this seat. It's given by some factorial homology of some factorial algebra for this seat. So, and similarly, you can say this is some factorial homology on the puncture disk. A better thing is to say it's factorial homology on S1. You need to be careful about the topology. You should get some pro algebra. So these things that are all affine. This is like in affine. You can write down explicitly what are the algebras or pro algebras. So therefore, for this calculation, you can just write it as some fractional homology followed by fractional homology followed by another fractional homology, which is equal to another fractional homology. That's what that is called AB lemma. So I don't or propagation property of fractional homology. So this is something. So on the for property 2, so the ingredient for this is Nick thesis. So in his thesis, he explained how to describe the modules on this thing using some from a consequential shift on this using some infinitesimal modifications, which we don't have time to do, and I will wait time for that. So that's all I can say now. Questions?
Okay, which is the property is roughly saying. What is it?
Okay, let me say it like this.
This is just this. Wait. The fact that you're doing, you found like a factorization homology or maybe whatever. It ends up being something like just all the last sections. But that's the global answer that these parallel photos. I heard homology to have.
Yes.
So in other words, the moral of the statement is that some spaces of rational sections are graphical.
Not necessarily that they're comparable, but that they're O homologies. Yeah, so like, if you can prove that this space is not regular uppers, sigma is contractible, things would be a lot easier. But at least the Durham homology protects the O homology.
I guess it's formal graphical. Like,
They think they're
at the end of the day, it's something it's something.
Yeah.
It's contractible. Yeah.
And I play model for this is like, back in the day, Dennis proved many examples where there are certain Z's, so for instance, very simple Z's like GN or something like this, the Jerome homology and the coherent homology are both behave like it's contractible. It's like some sense. Anyways.
Okay,
And that's sort of a picture of like an infinite dimensional projective space where the homology in both sides is going up to some and in both senses. And so
okay, let's leave this run magic to Q&A sessions. Now it's time for panel. Okay, so that's all.